Okay, please, Muntabihun, you can start the presentation.
Okay, thank you, Ananda. Assalamualaikum warahmatullahi wabarakatuh. Hello everyone. We are from Group 4. My name is Muntabihun and my partner Ananda Regina Prayitno. And in this meeting, we are going to explain about the applications of the supremum property. The first, we'll explain about the useful techniques in applying supremum and infimum. A. Taking suprema and infima of sets is compatible with the algebraic properties of R. Let S be a non-empty subset of R that is bounded above, and let A be any number in R. Define the set A plus S by set of A plus S for all A element S, or S element S. We'll prove that the supremum of A plus S is equal to A plus the supremum of S. The proof is, if we let U defined by supremum of S, then X is less than or equal U by the definition of supremum for all X element S. So that A plus X so that A plus X is less than or equal A plus U. Therefore, A plus U is an upper bound for the set A plus S. Consequently, we have the supremum of A plus S is less than or equal A plus U. And then next, if we if V is any upper bound of the set A plus S, then A plus X less than or equal V for all X element S. Consequently, X is less than or equal V minus A for all X element S, so that V minus A is an upper bound of S. Therefore, U equal to supremum of S is less than or equal V, which gives us A plus U is less than or equal to V. Since V is any upper bound of A plus S, we can replace V by the supremum of A plus S to get A plus U less than or equal supremum of A plus S. Combining these inequalities, we conclude that the supremum of A plus S is equal to A plus U equal to A plus supremum of S. The next useful techniques, if the suprema or infima of the sets are involved, it is often necessary to establish results in two stages, working with one set at a time. Suppose that A and B are non-empty subsets of R that satisfies the property A less than or equal B for all A element A and all B element B. We will prove that the supremum of A less than or equal the infimum of B. For given B element B, we have A less than or equal B for all A element A. This means that B is an upper bound of A, and that the supremum of A less than or equal to B. Next, since the last inequality holds for all B element B, we see that the number supremum A is a lower bound for the set B. Therefore, we conclude that supremum of A less than or equal to the infimum of B. The next, the application of supremum and infimum is in the functions. Suppose given a function f that map the set D into the set of all real numbers. We say that f is bounded above if the set f t equal to the set of all fx where x is element of t is bounded above in R. That is, there exists b element R such that fx is less than or equal to b for all x element t. Similarly, the function f is bounded below if the set ft is bounded below. And we say that f is bounded if it is bounded above and below. This is equivalent to saying that there exists p element R such that the absolute value of fx is less than or equal to p for all x element t. The examples. Next, we are going to present the example of the question supremum in function. Suppose that f and g are real valued functions with common domain D is the subset of R. We assume that f and g are bounded. A. If fx is less than or equal to gx for all x element t, then supremum of ft less than or equal to supremum of gt, which is sometimes written supremum of fx where x element t is less than or equal supremum gx x element t. We first note that fx is less than or equal to gx less than or equal to supremum of gt, which implies that the number supremum of gt is an upper bound for ft. Therefore, supremum of ft is less than or equal to supremum of gt. Hence, it is proved. The next example B. We note that the hypothesis fx is less than or equal to gx for all x element t in part A does not imply any relation between supremum ft and infimum gt. For example, if fx is defined by the square root of the x squared with t equal to the set of all x where x greater than or equal 0 and less than or equal to 1, then fx is less than or equal to gx for all x element t. However, we see that supremum of ft is equal to 1 and infimum of gt is equal to 0. Since the supremum of gt is equal to 1, the conclusions of A holds. Next, the third example C. If fx is less than or equal to gx for all x element for all x and y element t, then we may conclude that the supremum of ft is less than or equal to the infimum of gt. In the example B, uh, fx is less than or equal to gx for all x element t, we can we cannot conclude that supremum of ft is less than infimum of gt. But here, if fx is less than or equal to gx for all x and y element t, then we can conclude this relation. The supremum of ft is less than or equal to the infimum of gt. Okay, next. I'm sorry, I have lost my connection. We are going to continue the explanation. The next application is called the Archimedean property. The Archimedean property is like this. If x is element of R, then there exists an x element of the n, the set of natural numbers, such that x is less than or equal to nx, and here by x. The proof is by contradiction. If the assertion is false, then n is equal, oh, sorry, then n is less than or equal to x for all x element n, for all n element n. Therefore, x is an upper bound of n. By the completeness property, as last smoothing, the non-empty set n has a supremum u element r. Then we subtracting 1 from u gives a number u minus 1, which is smaller than the supremum u of n. Therefore, u minus 1 is not an upper bound of n by the definition. So there exists m element n with u minus 1 is less than or equal, I'm sorry, is less than m. And if we add 1 gives u less than m plus 1. Since m plus 1 element n also, this inequality contradicts the fact that u is an upper bound of n. Next, if S defined by the set of all 1 over n with 1 is with n element of the set of all natural numbers, then the infimum of S is equal to 0. Here is the proof. Since S is not equal, the empty set is bounded below by 0, it has an infimum, and we let W defined by infimum of S. It is clear that W is greater than or equal 0 for any epsilon greater than 0. The Archimedean property implies that there exists n element n such that 1 over epsilon is less than n, which implies 1 over n is less than epsilon. Therefore, we have W greater than 0 and less than 1 over n and less than epsilon. But since epsilon is greater than 0 is arbitrary, it follows from the theorem 2.1.9 that W is equal to 0. And if t is greater than 0, there exists nt element n such that 1 over nt plus greater than 0 and less than t. Proof: since the infimum of 1 over n for our n element the natural numbers is equal to 0 and t greater than 0, then t is not a lower bound for the set 1 over n for all n element n. Thus, there exists nt element n such that 1 over nt is greater than 0 and less than t. Next, if y is greater than 0, there exists ny element n such that ny minus 1 is less than or equal to y less than or equal to ny. Proof: the Archimedean property ensures that the subset Ey defined by all m element n, where m is greater than y of n, is not empty. By the well-ordering property, Ey has least element which do not by n way. Since this E-way is the subset of n, we use the well ordering property, then E-way has least element. And then n-way minus 1 does not belong to E-way. And hence we have n-way minus 1 less than y less than n-way. Collectively, these three corollaries 2.4.4 up to 2.4.6 are sometimes referred to as the Archimedean property of R. And the next application will be presented by my partner Ananda Regina Prayitno.
Okay, thank you, Muntabihun. Now for the next is the existence of square root of 2. So the theorem, there exists a positive real number x such that x squared equals 2. This is the proof. Let S defined by S element R, which S less than, S is greater than equals to 0, and S squared is less than 2. Since 1 is element of S, the set is not empty. Also, S is bounded above by 2, because if t greater than 2, then t squared greater than 4, so that t is not element of S. Therefore, the supremum property implies that the set S has a supremum in R, and we let X defined by supremum S note that X is greater than 1. We will prove that X squared equals 2 by ruling out the other two possibilities, x squared less than 2 and x squared greater than 2. Next, first assume that x squared less than 2. We will show that this assumption contradicts the fact that x equal to supremum s by finding an n in the set of natural numbers such that x plus 1 over n is the element of S, thus implying that x is not an upper bound of S. To see how to choose n, note that 1 over n squared less than or equal 1 over n, so that x plus 1 over n squared equals x squared plus 2x over n plus 1 over n squared less than or equal x squared plus 1 over n 2x plus 1. Hence, if we can choose n so that 1 over n 2x plus 1 less than 2 minus x squared, then we get x plus 1 over n squared less than x squared plus 2 minus x squared equals 2. By assumption, we have 2 minus x squared greater than 0, so that 2 minus x squared over 2x plus 1 is greater than 0. Hence, the Archimedean property can be used to obtain n in n, natural number, the set of natural number, such that 1 over n less than 2 minus x squared over 2x plus 1. These steps can be reversed to show that for this choice of n, we have x plus 1 over n is element of S, which which contradicts the fact that x is an upper bound of S. Therefore, we cannot have x squared less than 2. Now, assume that x squared greater than 2. We will show that then it is then possible to find m in n such that x minus 1 over m is the element of S is also an upper bound of S, contradicting the fact that x equals to supremum of S. To do this, note that x minus 1 over m squared equals x squared minus 2x over m plus 1 over m squared greater than x squared minus 2x over m. Hence, if we can choose m so that 2x over m less than x squared minus 2, then x minus 1 over m squared greater than x squared minus x squared minus 2 equals to 2. Now by assumption we have x squared minus 2 greater than 0 so that x squared minus 2 over 2x greater than 0. Hence the Archimedean property there exists m in n such that 1 over m less than x squared minus 2 over 2x. These steps can be reversed to show that for this choice of m we have x minus 1 over m squared greater than 2. Now if s in s, then s squared uh, I'm sorry, s squared less than 2 less than x minus 1 over m squared. Hence s less than x minus 1 over m. This implies that x minus 1 over m is an upper bound of s, which contradicts the fact that x equals supremum s. Therefore, we cannot have x squared greater than 2. Since the possibilities x squared less than 2 and x squared greater than 2 have been excluded, must have x squared equals 2. So this is proven. By slightly modifying the preceding argument, the reader can show that if a greater than 0, then there is a unique b greater than 0 such that b squared equals 1. B squared equals a. We call b the positive square root of a and denote it by b equals square root of a, or b equals to a of a power uh, 1 over 2. A slightly more complicated argument involving the binomial theorem can be formulated to establish the existence of a unique positive n root of a, denoted by the square root, the root n of a, or a power 1 over n for each n in natural number set. Next is density of rational numbers R. The density theorem. If x and y are any real numbers with x less than y, then there exists a rational number R in Q, uh, the rational number set, such that x less than R less than y. So this is proof. This is the proof. It is no loss of generality to assume that x greater than 0. Since y minus x greater than 0, it follows from corollary 2.4.5 that there exists n in n such that 1 over n less than y minus x. Therefore, we have nx plus 1 less than ny. If we apply corollary 2.4.6 to nx greater than 0, we obtain m in n with m minus 1 less than equal nx less than m. Therefore, m less than equal nx plus 1 less than ny. Thus, the rational number r defined m over n satisfy r less than x and r less than y. The corollary: if x and y are real numbers with x less than y, then there exists an irrational number z such that z greater than x, z less than y. This is the proof. If we apply the density theorem 2.4.8 to the real numbers x over square root of 2 and y square root of 2, we obtain a rational number r not equal to 0 such that such that r greater than x over square root of 2 and r less than y over square root of 2. Then z defined by r square root of 2 is irrational and satisfy z greater than x, z less than y. So this is the end of our presentation. Thank you for your attention, and we apologize for all mistakes of this presentation. So we are from Group 4, and thank you.